4 minus 25x to the negative 2 equals 0. So is that a quadratic equation? Is that a degree 2 polynomial equation as written? Blue, you shook your head. Why not? Yeah, because it's got a negative exponent, right? In fact, polynomials all have positive exponents, right? Just by definition, a polynomial has only positive integer exponents. And so we have to rewrite this with positive exponents if we really have any hope of solving it, right? Because we have not learned anything about how to like undo a negative exponent. But we do know how to rewrite with positive exponents, right? So how would I rewrite that? Yes?
This is just a different question. Can you just multiply through by a negative?
No, because that would change the signs of the coefficients, not the signs of the exponents.
Oh, it doesn't affect it.
Huh. Because remember, a negative exponent isn't a negative number. It means division instead of multiplication, right? So a negative isn't going to change that. We want to rewrite it just like we did when we did our exponent rules with a positive exponent, right? So how could I rewrite 25x to the negative second with a positive exponent? Yeah, so 25 times x to the negative second is the same as 25 divided by x to the positive second. And notice that only affects the one term, right? Like the 4 is off by itself. It's not being multiplied by any x's or anything like that. So it's not going to be involved in that fraction. It's just in the one term. And now I have an equation that contains fractions. So how do I deal with that? Yeah, we're going to clear fractions. So we'll multiply both sides by x squared. So I have x squared times 4 minus x squared over 1 times 25 over x squared equals x squared times 0. So we get 4x squared here, and then my x squareds are going to cancel there, and then anything times 0 is just 0. And now we can solve by factoring. So how do I factor 4x squared minus 25?
X plus 5, 2x minus 5.
Very good. So it's the difference of squares, so it factors into conjugates. You can do it the long way, like you can put that 0x in as your middle term and use the AC method. But difference of squares shows up so often, it's handy to know the shortcut, right? So we just took the square root of this, the square root of this became our two terms, and then the factors just differ by the operation between the two terms. One's positive and one's negative. And so equals 0. So we'll set each factor equal to 0. And we get x equals negative 5/2 and x equals positive 5/2. And one thing we kind of ignored here is that because this is an equation with fractions, like extraneous solutions are possible. Like we do have a restricted value of 0. But on these problems with the negative exponents, that won't ever be an issue unless you multiply by something other than the least common multiple. So if we had like multiplied by x to the third instead of x squared to clear fractions, we would have had an extra factor of x everywhere. And then we would have gotten x equals 0 as a solution, which we would have had to throw out because that's a restricted value. But as long as you use the least common multiple, so the smallest possible power of x to clear fractions, then that won't ever be an issue on these problems. So you shouldn't have to worry about it unless you're multiplying by way too many x's when you clear fractions. Any questions on this one? Okay, so I'm going to have you guys try this one. So solve, what did I say, 7x to the negative 1 minus 30x to the negative 2 equals negative 1. You want to use basically the same approach that we used on that last one. One more that's a little bit different, so let's solve x squared times x minus 1 squared minus 9 times x minus 1 squared equals 0. So if I want to solve this by factoring, what should I do on the left side? Yeah, and we can even factor out x minus 1 squared, right? Because they both have two factors. So we can notice that this is like two terms, and those two terms have a common factor of x minus 1 squared. So x minus 1 squared. If I pull it out of that first term, I'm left with x squared. I have subtraction between my terms, and then pulling it out of the second term gives me 9 equals 0. Because if I multiplied this all out, that would get really, really messy, right? And maybe even would give me a polynomial that we don't have the tools to factor. So we want to recognize this as sort of like a GCF problem, right? We have a greatest common factor of x minus 1 squared that we can pull out. And then we can factor that x squared minus 9 a little bit further. And then I'm going to set each factor equal to 0. But notice, like, x minus 1 squared is just x minus 1 times x minus 1, right? So I can really just write x minus 1 equals 0. I could write that twice if I really felt like it, but it's going to give me the same solution. So we get x equals 1, -3, and +3. And we don't have to worry about extraneous solutions or anything like that because there's no division or square roots in the original problem. So we have no possibility of having extraneous solutions. All good on that one? Okay, so now for the boring stuff. We have to write down some definitions. So an input for which a function's output is 0 is called a zero of the function. And what we start to notice is that we really just have lots of names for the same thing. In math, we really like inputs that make the output 0 because they help us do lots of things in very convenient ways. Like we'll find out later, like we can factor polynomials if we know the zeros of a function. And they also tell us what the x-coordinates of the x-intercepts are, right? Because remember that the x-intercepts of a graph have y values of 0, right? So the or the x-coordinates of those points are going to correspond to outputs of zeros, which is exactly what we said the zeros do, right? So the zeros of a function are also the x-coordinates of the x-intercepts of the function's graph. So to find x-intercepts and to find zeros, the process is essentially the same, but the x-intercepts and the zeros aren't the same mathematical objects. X or zeros are just x values, whereas x-intercepts are ordered pairs. They're points on a graph. So we can, let's see, for example, we would say 3 is a 0 of f of x equals x minus 3, because if I evaluate the function for an input of 3, I get an output of 0, right? 3 minus 3 is 0. So that's what it means to be a 0, is that if you plug it into the function, then you get an output of 0. So if I want to find, let's find the zeros and the x-intercepts of, what did I say, f of x equals x squared plus 4x minus 5. So like I said, we find the zeros and x-intercepts sort of starting the same exact way. We just want an output or a y value of 0, right? So we're going to replace f of x, our output, with 0. So we have 0 equals x squared plus 4x minus 5. And then we can solve that by factoring. So 0 equals x plus 5 times x minus 1. And so x equals negative 5 and x equals 1. So then when we state the zeros and the x-intercepts, the zeros are just the x values. So we say the zeros are negative 5 and 1. And then the x-intercepts are the actual points on the graph. So negative 5, 0, and 1, 0. So whether you're asked for the zeros or the x-intercepts, you're going to start that problem the same way, right? So we take the same approach for both. It's just the final answers that'll be different, right? So zeros, again, are just the x values, and then the x-intercepts are the actual points. So we can see this. So let's find those x-intercepts. So the x-intercepts of the graph of f of x equals x squared minus 5. So just like we did on the last one, we're going to set this equal to 0. So we have x squared minus 5 equals 0. But then we kind of run into trouble because we can't factor x squared minus 5. It's got two terms, but it's not the difference of squares, right? 5 isn't the perfect square. But if we think back to when we first started solving degree 2 equations, like the main problem we had, like if we wanted to solve it the same way we solve a linear equation by isolating x, the main problem we had was that we had an x squared term and we also had an x term, and we had no way to combine those into a single term, right? So we couldn't get all the terms. We couldn't get one term on one side containing the variable and then a constant on the other. But notice here, like I don't have an x term. I don't have that middle term. So I can get the one term that contains x on one side and then the term that doesn't contain x on the other side just by adding 5 to both sides. And then last week when we had functions that had square roots in them, how did we undo the square root? We squared both sides, so it stands to reason that we should be able to undo an exponent of 2. How? By taking the square root of both sides, right? So we're just using that opposite operation. So I have the square root of x squared equals the square root of 5. And then this is where it gets a little bit hairy. What did we say the square root of x squared was? Way back in the very beginning. So just the square root of x squared was what? Almost. Before we got to assume that everything was positive.
The absolute value of x?
Yeah, it was the absolute value of x, right? Remember, because if x was negative, remember we did it with like 5 and negative 5. Like negative 5 squared was 25, and the square root of that was positive 5. So we didn't get negative 5 out, right? We got the absolute value of negative 5. And so the square root of x is the absolute value of negative, or the absolute value of x. And then what numbers have an absolute value of the square root of 5? It's always weird when it's a square root. What numbers have the absolute value of 2? Yeah, 2 and negative 2, right? The absolute value of 2 is 2, and the absolute value of negative 2 is also 2. So the same is true even if it's a square root. So this tells me that x has to be the square root of 5 or the negative square root of 5. And all of that is just a really long way of saying that the number 5 has 2 square roots, right? Which we said all the way back at the beginning when we were talking about square roots, that every number has both a positive square root and a negative square root, and they were any number that could be squared to get 5. So we typically, when we solve these equations, we typically, whoops, not that part, we typically skip all of this, and we just say that x is both the principal and the negative square root of 5 is sort of the quicker way to get there. But that's why that is the case. And I mean, if you want to write the absolute value, more power to you, but it's sort of a long way to get to the same place. Yes?
In math lab, how do we put it in as the positive or the negative? Are we going to have to do root 5, comma, negative root?
So they actually added, you used to have to write them both, but they actually added a plus or minus symbol in there like a couple months ago when they did an update. So you can write it just like that, okay. Like the plus or minus. So that plus or minus symbol is just shorthand for those two solutions, right? One using the positive and one using the negative. The only time you need to separate them is if you're asked for like x-intercepts, so which we are here. So at this point, we would then say that the x-intercepts are the square root of 5, 0, and then the negative square root of 5, 0. So there's two separate points. So in that case, you want to write them as two separate points. So if it was just the solutions, you can use the plus or minus symbol. But you don't want to write two ordered pairs as like one ordered pair. So what we just used there is called the square root property. And we can actually extend it so that we can use it for more equations than like just equations that have x squared in them. If you have any equation where the left side is like something in parentheses raised to the second power and the right side is a constant, then you can take the square root of both sides. So then whatever that something is, is equal to plus or minus the square root of the constant. So this is kind of handy for equations like if I have x plus 3 squared minus 8 equals 0. So I could solve this by like multiplying that x plus 3 times x plus 3 and expanding the whole thing. But if I notice that this is just something raised to the second power, right? So some set of parentheses, doesn't matter what's in the parentheses, with an exponent on the outside, I can get the constant on the other side. Equals 8. So what you want to look for is the only thing on the left side that's outside the parentheses is that exponent of 2. Right? If there's anything else outside the parentheses, then the square root property isn't going to work. So I have something in parentheses, then the exponent of 2 is outside the parentheses, and then on the right side I have a constant. So we can take the square root of both sides. Remembering that on the right we want both a positive and negative square root of 8. And so we get x plus 3 is equal to, and we can simplify the square root of 8 as 2 times the square root of 2, right? Because 8 is 2 squared times 2. The square root of 2 squared is 2. The square root of 2 is 2. And then we're not quite done solving for x because we need to get that 3 out of there. So I'm going to subtract 3 from both sides. And we typically do operations on radicals on the left side of the radical rather than the right side of the radical. So that's why I didn't do this. Just because all sorts of problems can happen when you put it on the right side like that. Like the minus 3 likes to kind of sneak into the radical, and then you end up with something completely different. And so typically when we work with radicals and we do any operations outside the radical, we do it on the left side. So there's no ambiguity about if that number goes under the radical or not. And so those are my two solutions. Does that make sense? I was going to say something else about that one. What was it? Oh, yeah. Just by contrast, I want to go back to, like, if we're solving, like, x squared plus 8x minus, oh, I don't like that, 9 equals 0. I can't use the square root property here because the only thing that is something squared is this piece right here, right? And so if we tried to get everything else on the other side, if we look at the form it needs to be in, has to be something to the second power equals a constant, right? And this isn't a constant because it's got an x over there. And if I try to get the constant on the right side, I have that plus 8x that's in the way of my something squared, right? The entire left side is not something to the second power. So that 8x gets in my way no matter where I try to put it. It prevents it from being in that form. So I mean, like, if we could do that, we could have avoided all this solving by factoring to begin with, right? Like, and always use the square root property, but there's some equations we just can't use the square root property for because they're not in the right form. And we can't really, I mean, there's ways to put them in the right form. It's called completing the square, and it's super fun, but we don't do that in this class. So we won't do that in this class. It's so fun, though. And this square root property can be extended also to higher exponents. So we can solve say 2 times x minus 1 to the third plus 55 equals 1. And when I look at this, I think about using the square root property, which isn't really going to be the square root property. It's going to be like the cube root property. But I think of that because I see that I have something in parentheses raised to an exponent, and everything else outside of that is a constant, right? And so that's my clue that I might be able to put it in that form where I have something to some power equals a constant. And so I just need to get this guy by itself. So I'll subtract 55 from both sides. And then divide both sides by 2. And so now I have something to the third power equals a constant. How should I undo that exponent of 3? Yeah, we can take the cube root. So just like last week when we wanted to undo the cube root, we raised both sides to the third power. We're just doing that in reverse. So we have the cube root of x minus 1 to the third equals the cube root of negative 27. Should I have a plus or minus here? No, right? Because remember, the plus or minus comes from the fact that squaring a negative and squaring a positive gives you the same thing. That's why every positive number has 2 square roots, because if I square 2 and I square negative 2, they both give me positive 4. But if I raise 2 to the third power, I get positive 8. And if I raise negative 2 to the third power, I get negative 8. So I don't get the same thing from both the positive and negative. So every positive number only has 1 cube root. So that's why we don't have that plus or minus. That absolute value thing doesn't apply for odd index or odd exponents. So here we're just going to get x minus 1 is equal to negative 3, which is the cube root of negative 27. And then x equals negative 2 is my solution. Oops. So I want you guys to solve this one. Let's see. And when you've got your solution, show it to me. And you can go make sure you pick up your worksheet for tonight on your way out. It's right up here at the front. So solve 2 plus 54 x to the negative third equals 0. You're going to have to bring yourself back like 40 minutes to deal with that negative exponent. We cannot take a negative cube root of anything. Like, there's just no such thing as that. So we always have to get a positive exponent before we can even think about how we're going to solve it.